So we are on, I think this is 17th lesson. Let me just try to focus this thing. So in this lesson, we're going to be talking about energy and chemical change. I don't think it's going to be a long lesson, but I might be mistaken. So normally when you perform a chemical reaction in a lab, let's say you have your beaker. So that's the thing, you put your chemicals in and you add all your reactants. Let's say you have A plus B, those were your reactants. And your goal was to essentially produce a certain type a product, right? So we have, maybe in beaker one we'll have our reactants A plus B. You add the two chemicals and then they will give you some sort of a reaction where we have C plus D, or they'll give you some sort of a new chemical compound. This we call product. So in this side we'll have products, and on this side we'll have reactants. So there are many um, uh, chemical as well as physical properties that may take place, right? So you might find that maybe when you started in this beaker, when you added the things together, the chemicals were blue, and then after a while, after the products have formed, it's now red. This is just making a very basic sort of example, right? Cool. And then, but a lot of things also happen at the chemical level. And what we're going to be focusing mainly about today, mainly on up today, is the energy change that actually occurs during reactions. So there are two types of reactions that we're going to primarily focus upon, and that is so let me write the two types of those reactions where we have a sort of an energy change. So we have exothermic reactions, exothermic reactions, and then on the other hand, we may have endothermic reaction. So now what we're gonna try to attempt is to kind of differentiate between the two. So what type of reaction is an exothermic reaction? So during an exothermic reaction, these types of reaction actually are reactions that release, let me just draw a line here, that release energy, right? So they release energy. And then the opposite is true for endothermic reactions. These reactions absorb the energy, absorb the energy. Right. So if you were performing a sort of an exothermic reaction in a lab, and maybe you added something at the end of your, maybe you added your thing, what is it, your reactants in a beaker, and then at the end now you have your products. You'd actually, now if you felt the beaker, you try to touch it, you'd actually feel it that it has actually gotten slightly hotter. So it means that that reaction has somewhat released energy in the form of heat. So this energy that is released is in the form of heat. So this energy that can either be released or absorbed is in the form of heat. And that energy, we call it the heat of a reaction, or in other words, they call it enthalpy. So we call that the heat of reaction, or enthalpy, or a change in H. And you'll see later on when we draw graphs of both endothermic and exothermic reactions as a function of potential energy, you'll see how this actually, you can find it, right? And then for exothermic reactions, this change, this heat of reaction, this energy that is released, you'd find that it is negative. So it's lesser than zero. It means that it is negative, and it is measured in kilojoules per mole. For endothermic reaction, because this reaction actually absorbs the energy, that heat of reaction, or enthalpy, is greater than zero, meaning it's positive. So kg per mole. So let me try to explain what, if an example for this if you're given an equation. So if you're given an equation, they say A plus B, let's say, then they say this reaction there, B or C plus D. And then they write there on the side, the change in H is equals to negative 20 kilojoules or something. What that will be telling you, what that is telling you is that this reaction, because it's negative, this reaction is actually exothermic, right? And then if they give you a chemical equation, say they say A plus B, then it gives us C plus D, and they write there on the side the change in H maybe is just 10 kilojoules, right? What that is telling you that this is actually an endothermic reaction, right? So it's just very important to understand what this negative or positive enthalpy value means, right? So that you can know, is my reaction exothermic or is it endothermic? Does it release energy or does it absorb energy? So now you might be asking yourself like, okay, where does the energy um where does this energy that it releases comes from? So it can come from from maybe when the bonds that have been formed are broken. When they broken, so when you break those bonds, you may find that energy is released. And then in terms of where is this energy coming from that is absorbed by our endothermic reaction, this energy may come from the environment. You may as well maybe heat up or maybe a container that contains your reactants, and when you heat it up, it's essentially this reaction will absorb that energy, right? So very, very important for you to be able to define, what do we mean when we talk about an exothermic reaction? What do we mean when we talk about an endothermic reaction? What do we mean when we refer to the heat of a reaction or enthalpy, right? As well as being able to identify when a reaction is exothermic or endothermic using that our given enthalpy or heat of reaction value, right? Okay, so now we can actually further our discussion and say, okay, now we want to actually draw potential energy profiles of our endothermic or exothermic reactions. So in this instant, let us start with the endothermic reaction. So it's very important for you to be able to know this, to draw this graph, right? Or at least if you're given this graph, for you to be able to kind of, what is it, interpret it. So you're gonna draw both your x and y axis right there, and then on your y axis you will have potential energy, and it's measured in kilojoules. And then maybe on your left you will have nope, on your x-axis you have the cause of reaction. And let us say we were starting from, maybe you were given a specific chemical equation. It was A plus B, which gave us C plus D, and then they had written there that the change in H is greater than 0. So this was an endothermic reaction, right? So normally how I like to draw them, I like just drawing two dotted lines that are horizontal, and you'll see why now. And then just try to draw this graph here. So here you will have your reactants. So meaning here, my reactants in this case are A plus B. So my reactants are products. So here you'll have your reactants, which is A plus B. And then over there, so notice the energy of your reactants as well as the energy of your product. So on this side, you have your products. which will give it given by C plus D, right? So now there are a number of things that we can deduce from this thing. The first thing is I want us to talk about that heat of reaction. So the energy from here, from that product line up to that difference between the product line and the reactant line, right, is called the change in enthalpy. So this reaction, so the energy of the reactants was here, it absorbed this much amount of energy, and then you see that the energy of the products was actually greater than when we began, right? Cool. And another thing we can describe here is something called the activation energy. So the activation energy will come from the top here, and there at the top, we call that peak there at the top, we call it an activated complex. I don't have my duster with me, so yeah, this will have to do for now. And these markers are just so stubborn to wipe. So there at the top, I said that we have an activated complex. So activated complex, right? And then from the activated complex up until to what is it, your reactant line there, this is where you'd find your change in I'm like, it's not a change, this is where the value of your activation energy. But what is an activation energy? Activation energy, EA, so activation energy, EA, refers to the minimum energy that you actually require for a reaction to take place, and this is how you can essentially find it. But then sometimes we use a catalyst, and then why do we use a catalyst? We use a catalyst because we want to decrease the amount of energy required. So you see that we require a lot of energy for this reaction to essentially proceed, but then we want to lower that energy that we need. So it means that a catalyst will actually now lower our activation energy. And the interesting thing about a catalyst is that it doesn't actually get used up in the reaction. So when that happens, when we use a catalyst, you might have a graph that now looks like, I'm just going to draw the dotted line there to show that maybe now you see now our activation energy has actually been decreased. So you see our activation energy is now from there at the top to there. So we have actually essentially reduced or lowered the minimum energy required for this chemical reaction to proceed, right? So you must be able to draw this type of graph. But now, what does the one for exothermic reactions look like? So in the case of an exothermic reaction, we know that we'll have A plus B, right? Which will give us C plus D. However, our change in enthalpy will actually be negative because this reaction releases energy. So you will see here, so when our reactants here will start their energy level, they will have a lot of energy, and then you'll see that that energy is actually, it drops. So that's the energy released. So the energy released here, which is our heat of reaction or enthalpy, delta H, is that, right? Cool. So here we'll have our products, and then here we'll have our reactants, the energy. So we have A plus B, the potential energy of our reactants, potential energy of our C plus D, of our products, right? So we can still do the same thing. We can draw our activation energy. We said our activation energies is from the activated complex there at the top, that peak there, to the reaction line. So our reactions are here, reactants line, not reaction. So we have EA for our activation energy, right? Can still do the same thing. If we add a catalyst, it will actually lower the minimum energy required for this reaction to proceed. And then you find that our EA in this instant will just be from there to there. So the energy of our the activation energy will be lowered, right? So basically that is most of what is it that you need to know. So let us just try to compare the two. You should be able to also interpret these types of graphs and mention what is the activation energy, what is the activated complex, and understand the heat of reaction or enthalpy as we have shown, right? Cool. This brings us to the end of our lesson.